Hey there. So for today, these notes are going to cover pages 5 and 6 of our new unit number 9. So you should already have the new unit packet, should be creased open. And then I had given the sub instructions for you to do bell work number 1 already, just sort of getting you back used to remembering how to name chemicals and formulas or vice versa. All right, so if you want to go ahead and turn to page 5, concept 1 here is about writing formula equations from word equations. So you're going to be given the word equation, you got to write it in the formula. All right, so we want to identify and write formulas for diatomic elements as well as other, regular elements, but specifically diatomic is going to be kind of somewhat new to us today, but we've talked about them enough. And then also use the formula equation to write a word equation for a chemical reaction. So top of page 5. So a chemical equation represents a chemical reaction. So you're going to be writing down what is in white. So a chemical equation represents a chemical reaction. That's just telling you what is either breaking apart or coming together in terms of the chemicals in a reaction. So there's two sides to a chemical equation. There is the reactants side. So you see the arrow on the next line there. Make sure you write the word reactants here in white on this side, and then products, which are on this side or the ending. Okay, so reactants and products. Now, it doesn't mean that there always is 2 and 2. There could be 1 and 2, 2 and 1. There even could be 3 and 2, and different numbers. There could be more than one or up to 3. Okay. Now, below the arrow that's written in your notes there, write this word yields or yields. Sometimes I'll put it with an S. So you have the quotation marks that you can use there, and go ahead and put that right underneath the arrow. All right, there's a little bit of space there. So we read this as reactants, if you want to name your reactants, yield or yields your products. Okay, so reactants yields the products. Now, you might have different things above or below this arrow that we'll talk about later on in just a little bit here. But for the most part, it's always going to be the word yield that kind of comes into that. Now, you could have just one reactant in, a couple products or a couple reactants and maybe one product. Anytime you have more than one reactant or more than one product, you're going to separate them with a plus sign. Okay, that doesn't mean I'm separating reactants and products with a plus sign. That's done with the yield sign. But if I had, blank plus blank and then yields blank, so I would add a plus sign to separate my my couple of reactants from each other. So common forms of chemical reactions. These are just sort of basic formats that chemical reactions can happen in. So I'll have you write these down. Now we're just writing them in like an A, B, C, D format. Those represent the different chemicals. Okay, so we're going to make it kind of simplified here. So you could have a formula look like this, where you have 2 reactants, A plus B, and yields C. So go ahead and write this down in the middle of page 5. There's not a box or a line or anything, but it's right after the ... So this is one format that you might see it in. A plus B yields C. Another format might be this. A yields B plus C. All right, the arrow always goes this way. All right. And then another way that we can write it is where we have 2 on the 2 products, or sorry, 2 reactants and 2 products. It could be written like this: A plus B yields C plus D. So that would indicate another arrangement. Now there can be more than 3 products or more than 2 products or 2 reactants. Sometimes we could have up to 3 reactants or products. Generally, we're just going to keep it simple and probably just have more, at the most two. So 2 and 2, but just be aware of that. There's possibility that some reactions might yield 3 products or have 3 reactants. So chemical equations can be written as word equations or formula equations. So write this down on that line there in the middle of your paper. So chemical equations can be written as word equations or formula equations. And word equations are never balanced because we don't use the coefficients in the word equations. Formula equations can or cannot be balanced, and you guys kind of know what balanced means. We worked out that a little bit last week before we left for break. So formula equations can be balanced or unbalanced. For right now, assume that you have no idea about balancing as we kind of start off this unit together here. And we'll kind of work on balancing when we talk about our next concept 2. But for right now, we'll kind of assume that we don't really understand the balancing yet, even though I hinted at it already. So formula equations can be balanced or unbalanced. It kind of depends on what I'm looking for. So here's a word equation. Iron plus oxygen yields iron 3 oxide. So notice that I have iron plus oxygen and then yields iron 3 oxide. So this would be A plus B yields C, even though that's a 2-part name, 3 if you include the Roman numerals, it's still, one product. Now what the formula equation looks like here is I would have to turn iron into a formula. Iron just as Fe. Oxygen actually ends up as a looking like this, O2. And iron 3 oxide is written like this, Fe2O3. So how do you know what these are going to look like? Well, iron is just a monoatomic ion. I'll kind of explain that here in a second. So that's just written as Fe. The oxygen is actually diatomic, so we write that as O2. We'll again explain that in a little bit more. Iron 3 oxide, though, you should be able to get. Remember that iron 3 means that the iron has a plus 3 charge. So if I were to write this, I would write like Fe plus 3. And oxygen has a charge of -2. So I would write that as O -2. And then you cross charge them, right, to get 2 irons and 3 oxygens. So that has to do with cross charging again, but recognizing that iron 3 means the iron has a +3 charge, oxygen has a -2 charge. Now, when you look at it down here, there's a couple things. All right, you'll see these this information here in parentheses. Those are going to represent states of matter. S is solid, G is gas. So the iron is in its solid form. The oxygen is in its gas form, and iron 3 oxide is rust in its solid form. We'll get to a little bit more about those meanings here in a little bit. Now, that was the unbalanced version of that. I'll just go back here quick. Okay, but you can see, if you remember from last week, the Fe over here, I have 2 over here, so that's not balanced. My O2 here, I have 3 here, that's not balanced. So remember that I have to use coefficients to balance them. You don't have to write this in. Don't write these coefficients in yet because you don't necessarily need to know it right now for this lesson. But this is what it would look like balanced. So you would have to have 4 iron atoms, 3 O2 atoms, and you would end up with 2 iron oxide atoms. This is completely balanced now. So don't worry about this yet. Don't have to write that in, but I just wanted you to know that's kind of where we're headed. So let's get back to some of these symbols. Again, we have the SLG that stands for solid, liquid, and gas. All right. Now, beyond right here, I don't think a lot of our examples in here actually use them. I might have us kind of continue to put them in periodically, like based on where they kind of fit. But, for the most part, I mean, you can kind of assume that if it's a, unless you're given more information, sometimes you're not going to really know if it's maybe a solid form or an aqueous form, which is what AQ stands for, right? So for right now, we'll just kind of hold off on using these a lot, but I just want you to know what they are because sometimes you'll see them in formulas like on ACTs and things like that. So AQ we've already talked about, means aqueous, means that it's dissolved in water. Now, being that it's AQ and it's dissolved in water, usually the H2O, even though it is technically, part of whatever is dissolved in it, we don't usually include H2O in the chemical reaction unless it actually plays a role in the chemical reaction, which oftentimes it doesn't. Usually it's just the solid particles in there that are playing a role. So a lot of times, even though it says aqueous, we're not going to include water as part of the either reactants or products. Now, if you see a double-sided arrow like this, it means that the reaction is reversible, which means that you can take the two products, combine them back together to create your two reactants, right? That doesn't happen for everything. Most of the times when reactions are complete, they are complete, but there are some that can be reversed. With this one, you're going to have to add a couple things here. So you have the two arrows here, but you have to add these symbols or words above them. So above the first arrow here in the box, you'll have to put a little triangle. That usually means change in, or in this case, thermal. And over the second one, write the word heat. So there are reactions where heat is needed in order to get the reaction to occur. It just doesn't occur without it. So a lot of times we'll use a symbol or the word to show that that is also involved in the reaction. And then the last one here, I'm putting the letters PT over here. PT is an element, platinum. It doesn't always have to be platinum. It can be any element. But this represents, if you see an element over the arrow, it usually represents a catalyst that is added. And a catalyst, if you remember from maybe Miss Reinhardt's class last year in biology, might have talked about enzymes and proteins. And enzymes are proteins that speed up reactions. They help reactions go faster and take less energy. And a lot of times a catalyst is needed to attach to that enzyme to sort of activate it. And so that enzyme or catalyst here in this case is listed down as part of the equation, but not like part of the reaction, but not necessarily part of the equation. So we're not going to have to worry about balancing it. We're not going to have to worry about figuring out how many, like the coefficient number of it or anything like that. So just remember that you could see a reaction written like that. Okay. So the next page here is all stuff that we have talked about as part of our unit 7, which was naming. So most of this stuff is all, just stuff that we've already covered. It just need to kind of be refreshed on it. So to change word equations into formula equations, you're going to kind of follow this flow chart. So there's two questions that you can ask when you see a word. All right, is that substance an element? Or if you look down below, is that substance a compound? So you have to first decide, is it an element or a compound? Key thing, element will be written as a single word, all right, just by itself. Compounds are usually written as, either a 2 or a 3-part word, just based on, if it's a polyatomic ion, it might have 3 different parts, but at least 2-part name. So if it's a 2-part name, that's a compound. If it's a 1-part name, it's going to be an element. So then you need to decide, is that element monoatomic or diatomic? Mono means one, means there's only one atom of it. Doesn't mean it can't have a coefficient, but it means that you'll just have it by itself. So if you have decided that it's monoatomic, and I'll give you, basically you're just going to have to decide, is it diatomic? No, then it's monoatomic. You just write the symbol. All right. So monoatomic includes all your metals. So I have the example here of sodium. So if you just see the word sodium, it's just Na by itself. No 2, no 3 subscript behind it, not any 2, not any 3, no subscripts behind them, but they may have coefficients when you balance them. Okay, so don't be aware of that. They may have a number in front of them, but you won't worry about that until you're balancing. So that includes all your metals, all your transition metals, anything like that. It also includes some nonmetals. So if you saw like phosphorus or sulfur, they would be written just with a P or an S. Now, diatomic molecules include these. These are ones that are form gases usually, and so they always need to be to form a bond with themselves. So these are our 7 diatomic molecules: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So these go on the first bullet point under the diatomic box there. So those are the 7 different examples. When you see them written, though, you're going to see bromine, iodine. It's not going to be written like diiodine or dibromine or dinitrogen. You're not going to see the word di in front of it. It'll just be written as the element itself. They will have the subscript 2 behind them. Okay, so I'll have you just go ahead and write these examples down. So again, you're not going to see it. You're going to see the actual name of the element listed: bromine, hydrogen, chlorine. You're not going to see chloride or fluoride. All right, those are we only use IDE endings when we are making bonds between either ionic compounds or molecular compounds. So it'll actually be bromine, or bromine, I guess, iodine, nitrogen. So no nitride, no chloride, no oxide. All right. So your first job is, when you see a single element by itself, is to ask, is it diatomic? If it's diatomic, if it's one of these 7, you will write it as that letter with 2, the subscript 2 behind it. If it is not one of these 7, it's going to be monoatomic, and you just write it as the symbol. And you can also still put coefficients in front of these, but they're going to always have to go up by 2s. Or I just mean the number of atoms. They're always going to have to double by 2s. Okay. Now, if your substance that's listed in the word problem is a compound, and you'll know that because, again, it'll have like a 2 or possibly 3-part name, more than likely 2 though. Your first step is to decide now, or your next step is to decide, is it ionic or molecular? So ionic usually involves metals and nonmetals, okay? That's what the M and the NM stand for. And you can write that right behind the word ionic in the box in the middle of page 6. Now, it is possible that you might not always have a metal as part of your first atom there. Sometimes, we might have, like we do have ammonium, which does have a charge of +1, but it's a polyatomic ion. So just be aware of that it's a small chance that it might not necessarily be a metal. But metals and nonmetals, look for ionic ones. So again, when you put these into formulas, you need to balance their charges by looking at cross-charging. Okay, so for example, calcium chloride. Calcium has a charge of 2+, right? It's in the second group. Chlorine has a charge of -1. So when you cross-charge them, 1 goes with the calcium, 2 goes with the chlorine, all right, and you end up with CaCl2. So cross-charging is what we're going to be using to put your ionic compound into a formula. Remember that you need to reduce, though. So if I had 2 and 2, I would need to reduce that to 1 and 1. Now, molecular compounds are always going to have a nonmetal bonded to a nonmetal. So a single nonmetal bonded to a single nonmetal. Remember, ionic compounds can also include polyatomic ions. So we need to keep that chart, polyatomic ion chart, in our back pocket here too. So molecular ones, the ones that set these apart, or that I always kind of look for, is prefixes. So you have to, in order to name these, we need prefixes for the subscripts. Now, remember, these are always going to be two-part names. Okay, so it is possible that the first word, if there's just a single atom of it, won't have a prefix in front of it. But the next letter will. So like NO is nitrogen monoxide, right? NO is nitrogen monoxide. The word mono is in there as a prefix, and that kind of gives me a clue that that is a molecular. So dinitrogen tetraoxide. So you're looking at dinitrogen is N2, tetraoxide is O4, and we do not reduce these. So dinitrogen tetraoxide is N2O4. No reducing. Remember, the first word may not have a prefix with it, but the second word always will. So if you see no prefixes, that's probably your clue that it's ionic. Okay. So now let's do some examples. On the bottom of page 6 here. So we're converting these into formula equations. So we have sodium chloride plus fluorine yields sodium fluoride plus chlorine. Notice my use of fluorine and fluoride, all right, chloride and chlorine. All right, sodium chloride is the IDE ending tells me that this is a bond of some sort, whether it's ionic or molecular. I'll have to figure that out. But fluorine and chlorine tells me that they're by themselves. Those are single elements. So I'm going to have to decide if they're monatomic or diatomic. So sodium chloride. All right, sodium is a metal, chloride is a non-metal, and so that is going to be an ionic bond. So I need to use charges for this. Another clue, no prefixes, right? So it's got to be ionic. So I have Na plus 1, chlorine plus 1, cross charge those 1 and 1. There's my first formula. Most of you know that. Then plus. Now fluorine, remember fluorine, I need to look that up. Is that monoatomic or diatomic? That's a diatomic one. So that's going to be F2. F2, not the 2 in front. 2's got to go behind it. And then yields, make sure you copy the arrow with it here, and the plus sign as well. Sodium fluoride, I'm going to use the same thing. Is this ionic or molecular? Ionic, because there's no prefixes. So Na plus 1, fluorine minus 1, cross charge them 1 and 1, NaF. Chlorine is an element, right? Monoatomic or diatomic. It's diatomic, so it's Cl2. Now this isn't balanced. We have 1 Cl here, 2 Cls here, 1 fluorine here, 2 here, but we'll get to that in our next unit or our next concept. Next one here is aluminum plus sulfur yields aluminum sulfide. So these are my two reactants, aluminum and sulfur. Aluminum is so it's an element, right? It's monoatomic because it's not one of my diatomic ones, so it's just Al plus. Now, S is technically a nonmetal, but it is not one of my diatomic molecules. It's not listed as diatomic, all right? So that one is just an S by itself. Now, aluminum sulfide, this is where I got to use my charges to figure out what aluminum sulfide is. So again, I know that it's ionic because there's no prefixes. So aluminum has a charge of +3, sulfur has a charge of -2. Cross charge them, you get Al2S3. Again, not balanced, but that's okay. So you want to kind of remember to try to keep your substances or your plus signs and your yield signs lined up with each other. So I usually like to do that, even if that means a lot of spacing in between. I personally like seeing the arrows line up and the plus signs line up with each other. So you guys can go ahead and do that too if you want. You'll have a lot of space in between, but that's okay. That also leaves you room to add coefficients when you need to. All right, so let's look at the last one here. We have zinc sulfide plus magnesium arsenate yields zinc arsenate plus magnesium sulfide. So zinc sulfide, again, no prefixes, so this tells me it's ionic. Now I need to look up zinc on my periodic table. Zinc has a charge of +2, and it's not, even though it's a transition metal, it's not a multiple different charges. Its only charge is +2, so that's what all I need to use. So this one does not include Roman numerals, but you will see some Roman numeral ones in your other problems. So Zn +2, S -2. When I cross charge them, I end up with 2 and 2, which reduces to 1 and 1. ZnS plus magnesium arsenate. Now be careful. Arsenate might sound like arsenic, and you might just go with AS, but remember AT. That ATE ending tells me that that is a polyatomic ion, so I need to use something different. Okay, so I have magnesium, which has a charge of +2, and then I need to look at my periodic table for my polyatomic chart to figure out what arsenate is and its charge, AsO4. Now that has a charge of -3. When I cross charge these, I'm going to need 3 magnesiums and 2 arsenates. That means I have to use parentheses. Parentheses are not optional. So that is going to yield zinc arsenate. Again, zinc has a charge of +2. Arsenate, I just wrote down over here, ASO4 with a charge of -3. So I'm going to write that down, or at least get the charges written and cross them. So Zn +2 and cross with ASO4. So that'll be 3 zincs I need from that cross charge there and 2 arsenates plus magnesium sulfide. So this just goes back to what is the magnesium? Sulfur, sulfide, 2 and 2, which reduces to MgS. All right. So with that being said, what I'm going to have you guys do for today is work on pages 7 and 8. 7 and 8 on, so don't worry about the exit ticket right now. I just want you to begin worksheet number 1, page 7 and 8. You should be able to get a start on those. Again, you're not balancing yet, okay? You're not balancing yet. If you get done with them and you want to, because you kind of know how to do it, go ahead, but you do not have to balance them yet. All right, that's it for me today.